Yan, ma'am. Audible na po, ma'am.
Yes, sige.
Yan, ma'am. So, my topic is pharmacokinetics of oral drug absorption. So, when I was given this topic po, medyo nalito ako sa, akala ko PKA, ma'am, ng PH. So, very broad siya na topic. Kasi pharmacokinetics, madami siya under drugs, physicochemical properties. So, ito lang based sa mga na-research ko po, or ito lang parang summary. So, pharmacokinetics of oral drug absorption is determined by the drug's physicochemical properties, formulation, and route of drug administration. So, ito yung mga factors ng oral drug absorption. So, first are the dosage forms, the tablets, the capsules, are the solutions. So, these drugs and its ingredients are formulated to be given by various routes. Regardless of the route of administration, drugs must be in solution to be absorbed. So, solid forms such as tablets must be able to disintegrate and deaggregate for it to be absorbed. So, absorption is the movement of a drug from its site of administration to the bloodstream. The rate and extent of drug absorption depend on multiple factors such as the administration, the formulation, and drug-food interactions. So drug absorption from the gastrointestinal tract or any other extravascular site is dependent on physicochemical properties of the drug and the environment in the small intestine, the dosage form used, and the anatomy and physiology of the absorption site, such as the surface area of the GI tract, stomach emptying rate, GI mobility, and blood flow to the absorption site. So extravascular drug delivery is further complicated by variables at the absorption site, including possible drug degradation and significant inter and intrapatient differences in the rate and extent of absorption. The variability in drug absorption can be minimized to some extent by proper biopharmaceutical design of the dosage form to provide predictable and reliable drug therapy. So most drugs are weak organic acids or bases existing in unionized and ionized forms in an aqueous environment. The unionized form is usually lipid soluble and diffuses readily across cell membranes. The ionized form has low lipid solubility and high electrical resistance and thus cannot penetrate cell membranes easily. Theoretically, sa pH naman, weakly acidic drugs such as aspirin are more readily absorbed from an acid medium than weakly basic drugs. However, whether a drug is acidic or basic, most absorption occurs in the small intestines because the surface area are larger and membranes are more permeable. The proportion of an ionized form and thus the drug's ability to cross a membrane is determined by the environmental pH and the drug's pKa, or the acid dissociation constant. The pKa is the pH at which concentrations of ionized and unionized forms are equal. When the pH is lower than the pKa, the unionized form of a weak acid predominates, but the ionized form of a weak base predominates. Passive diffusion. So drug diffuse across a cell membrane from a region of high concentration to the low concentration. So diffusion rate is directly proportional to the gradient but also depends on the molecule's lipid solubility, size, degree of ionization, and the area of absorptive surface. Exchange diffusion is defined as the movement of solids across a in fluid moving in an opposite direction. And facilitated diffusion is the passive movement of molecules along the concentration gradient. Active transport is among the mechanisms that transport proteins and move compounds, including drugs, into and out of the cells. So transport proteins are located at the portals of entry, where they attempt to ensure that xenobiotics do not enter the protective tissue. So active transport seems to be limited to drugs structurally similar to endogenous substances such as the vitamins, sugars, and amino acids. These drugs are usually absorbed from specific sites in the small intestine.
Ma'am, sige.
Absorption describes the journey of a medicine or transfer of mass from the site of administration across biological barriers to site of action or site of measurement. So absorption can be described using two factors, its extent and the rate. The extent describes the total amount of drug entering the body, and it is independent of time, so the units here are in mass. While the rate describes how quickly the drug enters the body, and the units here are um, have a time quality. So the extent of oral absorption. The extent of oral absorption can be considered in two parts. The first part is the fraction of drug absorbed across the gut wall. This describes how the drug gets into the portal vein from the gut, and physicochemical properties of the medicine can impact the fraction absorbed. Small, unionized molecules are mostly completely absorbed across the gut wall. Large and ionized molecules cross membranes with difficulty, and only a small fraction is absorbed across the gut wall. Fraction absorbed may be influenced by the metabolism drug in the gut wall, such as simvastatin by CYP3A4, or transporters which move drug back into the gut lumen. The second influence on extent is its first pass extraction. Some of the drug may be extracted by hepatic enzymes, and this is influenced by organ clearance as well as blood flow. The extent of absorption is therefore the amount of an oral dose that crosses into the portal vein and which survives the first pass extraction. The rate of absorption, it may be described in we can describe processes as first order if they are dependent upon concentration. So if absorption follows a first order process, then a constant proportion of drug is absorbed per unit time. This one compartment model describes first order absorption and first order elimination. Therefore, the rate is in proportional to the amount of drug in the gut, and the rate out is proportional to the amount of drug in the central compartment. First order process can be used to describe diffusion across the intestinal membrane that is concentration dependent. The rate of diffusion is related to the concentration, therefore a higher rate can be observed at a higher concentration. So the zero order absorption is seen with controlled release dosage forms as well with poorly soluble drugs. The rate of input is constant, while first order absorption it is seen with the majority of extravascular administration such as oral, intramuscular, subcutaneous, rectal, and most pharmacokinetic models assume first order absorption unless otherwise stated. So zero order reaction, and the reaction rate is independent of the concentration of the reacting substance. First order is when the reaction rate depends on the first power of concentration of a single reactant, such as absorption, distribution, and elimination rates. And the second order is the rate of change in concentration of product and reactant independent on second power of concentration of a single reactant. Majority of drugs are administered orally rather than via a parenteral route. The rate and extent of oral absorption can be influenced by the physicochemical factors of the medicine and the physiological factors of the patient. So following the oral administration, the drug must disintegrate and dissolve in the solution before it can cross the gut membrane. In order to cross the membrane, the drug must be soluble in the lipid material of the membrane, such as well as aqueous phase. Most medicines will not be absorbed in the stomach and require passage to the small intestine before diffusion in the circulation. Stomach emptying time can influence acid degradation and delay absorption. A fatty meal or cold food can slow stomach emptying rate. Concomitant medications can decrease or increase stomach emptying time. So, for an example of a medicine that can decrease stomach emptying time is morphine, and metoclopramide can increase the stomach emptying time. The difference between rate and extent of absorption, a delay in gastric emptying may mean a decrease in the rate of absorption, but the extent of absorption may remain unchanged if the medicine does not degrade in the acidic environment of the stomach. The lag time, the time course of concentration with absorption beginning at the time of administration. This assumption requires further refinement. So disintegration and dissolution transit to absorption sites and transfer across the absorption site are all factors that can contribute to absorption delay. A lag time allows quantification of the time delay between administration of dose and commencement of absorption. A simple approach to the shift of the curve using a lag time so that absorption begins after administration. Lag time may be then another may be considered another parameter that we wish to estimate. Thus, each individual may have a different lag time. As of sa computations, ma'am, sa dami ko nakitang computations, hindi ko na alam anong kailangan, anong important, ma'am. So, yun lang po, ma'am. Thank you.
Okay, thank you. Actually, we have a lot of computations on this, no, but let's just have the common ones, and I think it's not really practical for us to go deeper to the complicated ones sa sa itong route na ito. But anyway, wait lang ha. May kasama ka sa report na ito? Tama,
yes,
no?
ma'am. Ma'am Nyala.
Okay, sige. Let's move into that before I'll give some supplication na lang.
Wait lang po.
Andito na siya, no? Ayan na.
Ma'am, nag-chat siya kasi na ako na lang daw muna mag-report kasi nagpa-check up pa ata siya, ma'am.
Okay. Sige, go.
Yes po. Ay, ma'am, okay na ba, ma'am, if mag-move na lang po sa next na reporter po? I-contact ko muna siya, ma'am.
Okay. Sige, wait, ha?
Ma'am Reza, ang kapartner ko wala din po siya.
Asa naman
Sa Zamboanga po kasi it's raining, so maybe it's affect the connectivity po ng kanyang
Okay, sige.
Yun po. So I will proceed with my part, ma'am. Okay lang.
Okay, sige, go.
Okay. But I will try my best, ma'am, kasi most of it are figures.
Okay. Okay, sige.
Okay. Play na ba? Okay, yes. Good afternoon, everyone. In behalf of IMAN, I will be reporting about pharmacokinetics of IV infusion. So let me share our notes, literally notes. So It consists of introduction, model representation, the first compartment, two compartment, and the description of each model, then some equation, then a summary, then a references that we use. Then next, first, this one, IV infusion. We say IV infusion, drug administered to the intravenous route at a constant rate over a determined interval time. So even before you are not yet under IV, rate infusion is greater than the rate of elimination. But once you're under IV, it will be equal. Rate of infusion will be equal to rate of elimination. So having said that, rapid IV injection is unstable when the drug has potential precipitate toxicity or when maintenance of a stable concentration or amount of drug in the body is desired. In such a situation, the drug, for example, several antibiotics, theophylline, or procainamide, is administered at a constant rate, meaning when we say constant rate, it's a zero order by IV infusion. In contrast to the short duration of infusion of an IV bolus, meaning IV bolus is few seconds lang yung effect, the duration of constant rate infusion is usually much longer than the half-life of the drug. So the advantage of this zero-order infusion of drug, it includes it ease of control of the rate of infusion to fit individual patient needs. Then second, it prevents fluctuating the peak and valley of the plasma level. Then third, other drugs, especially electrolytes and nutrients, can be conveniently administered simultaneously by the same infusion line in critically ill patient. So dito naman sa second page, sa plasma concentration, when we say CSS or steady state level, it means when the drug is infused, dito mag-start. When the drug is infused intravenously at a constant rate, and then a plateau, this is a plateau, this is a steady state rate, meaning it reaches already the steady state rate. So that's what it means, a steady state rate level. So meaning yung concentration is already reached progressively. Then next, one order infusion. The one order infusion, the pharmacokinetics of this one, this one is by constant IV infusion followed a zero order input process in which the drug infused and directly sa blood dito. And then, for most drug, ang elimination drug of the plasma is the first order, which is yung sinabi ko kayo na first order elimination rate, which is equivalent to KE. Then, zero order rate of that is equivalent to RO. So therefore, this one compartment model, the infused drug follows zero order input and first order output. So the change in amount of drug in the body at any time during the infusion is the rate of input minus the rate of drug. So yun yun. Description. The entire body is considered single compartment. Ito. Highly perfused or low perfused organ and well-wide variety of tissue are concerned as equal or uniform. Since it is IV infusion route, drug is directly entered into the body. So there's no absorption. It will not pass through the digestive system. So the rate of infusion, which is KO, exists and always follow a zero order kinetics, which is there is always an elimination. Since this is open, means there is always an elimination. So elimination follow first order linear kinetics. So yun yung description ng one compartment IV infusion. Then for the rate of drug presentation in the body, at any time during the infusion, the rate of change in the amount of drug in the body. For example, dx and dt is the difference between zero order rate of drug infusion, which is the yung RO, and first order rate elimination. So ito yung parang standard na equal, constant. Then when we arrange that one, ma'am, sorry ma'am ha, kay nalito din alaga ako ma'am. So when we arrange that one, KE ang X. So ito na yung parang arrangement niya from this first formula, wherein ang X is equivalent to BDC, this one. So pag ito siya equivalent kay BDC, yun yung BDC. Pag na-rearrange na siya, the BDCX will be here down. So ito na yung next na formula na mangyayari. Since ang KEVD is equivalent to CLT, so masu-shorten siya, ma-convert siya into CLT, which is here. So yun yung parang formula niya. From here, it will be like this. So sa IV infusion, keep in mind na slowly increasing then slowly decreasing siya. So from here, you can see, wala pa yung pinasok na drugs, wala pang elimination na mangyari. But after some time, pag meron na yung na-infuse na medicine or drug, slowly magbi-build up na yun doon sa compartment niya until ma-reach niya yung steady state. And then pag nag-stop, mag-lower na naman hanggang sa after a few days, pag mag-stop the infusion, totally clear na yung wala na siyang ma-eliminate. So yun yung parang explanation when administering an IV infusion. Mag-reach siya sa zero, then mag-build up yung sa body hanggang sa ma-reach na yung steady state. Then pag i-stop siya, saka siya mag-lower kasi may elimination man, hanggang sa totally ma-clear na ma-eliminate na lahat yung na-administer through IV infusion. So steady state plateau or infusion equilibrium. Sa steady state plateau, kung titingnan nyo dito sa first, on the starting of the saan ba yun? Ito, plateau. Okay. There is no drug dito. So to start dito, there is still no drug. So the body therefore is no elimination na mangyayari. Sorry. Then at the constant rate, the amount of drug in the body is zero. Hence, there is no elimination. As the time passes by, paakyat yan siya. Yun yung explanation ko kanina. As the time passes, aakyat siya. Then it rises gradually until it reaches a certain point of equilibrium dito. Yung dito niya. And then, automatically, magda-drop na naman siya kasi there is elimination. So, yun yung parang steady state plateau yung dito na part. So, this graph explains that the plasma concentration versus time profile of a drug given by a constant rate of IV infusion. This is a constant IV infusion. So, when we say steady state, it is rate of infusion equals rate of elimination. And then, ito naman yung formula. At a steady state, the rate of change is amount of drug in the body is zero. Hence, the first equation becomes, this is the first equation. So, pag na-rearrange siya, this will be the equation. Then, kapag ito naman ang hanapin natin yung steady state, pag ma-rearrange siya, ito yung equation. Then, kapag basta mag-rearrange lang siya ng equation niya. Then we all know that CL is equal to KdV. So, ito yon. So, ang final equation nitong steady state is itong CL. Means, eto, infusion rate over clearance. So meron akong one later, parang summary, so that hindi tayo malito. So from this equation, CSS is the amount of drug in the body at a steady state, where CSS is the concentration of drug in plasma at a steady state. So the value of this elimination rate can be obtained from the slope, this one. And then on a straight line, after a semi-logarithm plot, which is log C versus T of the plasma concentration, time data gathered from the time when infusion is stopped. So alternatively, this one, KE can be calculated from the data collected during the infusion to steady state as follows. This one, the substitution. This is the original formula from the previous equation, then it will yield from this. Then we all know that CSS is equivalent to this one, RO versus CL over T. So when we rearrange, it will yield like this. Kasi this one, you will replace this with this, ROCLT. And then again, you will convert it into log form, which is this. Then a semi-log plot of CSS is minus C versus CSS versus time, result in a straight line with a slope of KE. So this one, the graph tells you that the semi-flat for compute of KE from infusion data up to steady state. Then for the percent of steady state attained at the end of a given half-life. So this is the sample. The time to reach steady state concentration is dependent upon the elimination half-life and not infusion rate. So ito yung half-life. Then the increase in infusion rate will merely increase the plasma concentration attained at steady state. For the therapeutic purpose, greater, it's more than 90% of the steady state drug concentration in the blood is desired, which is reached in 3.3 half lives. It takes 6.3 half life for the concentration to reach 99% of the drug of the steady state. Thus, the shorter the half life, sooner is the steady state ma-reach na. Then for the infusion plus loading dose, it takes a very long time for a drug having longer half-life before the plateau concentration is reached. One of the example is phenobarbital, it will take 5 days. Initially, such drugs have subtherapeutic concentration. This can be overcome by administering an IV loading dose large enough to yield the desired steady state immediately upon injection prior to the starting the infusion. It should then be followed immediately by IV infusion at a rate enough to maintain this concentration. So this graph is an IV infusion with loading dose. As the amount of bolus dose remaining in the body falls, therefore, it's an explementary rise resulting from the infusion. Dito. Then next. So the formula is this. Recalling once again the relationship of X is equals to BDC, then the equation for compounding loading dose is XO can be given like this. Then we all know that CSS is equal to this. So you have to replace that one with this. So eto na yung result ng formula ng KOL. Ito po. So the equation describing the plasma concentration time profile following simultaneously IV loading dose and constant IV infusion is the sum of two equations describing each process, which is this one. Since we all know that KO is CSSBD, which is this one, and CSS is equal to KED, which is, and RO is equivalent to CSS times KEVD, volume of distribution. After replacing X, this one, and RO, and simplifying, we will get the C is equal to CSS. So, yun yung mga formula, medyo makalito. So, and let's summarize those formula from this one. So, when we say rate of the drug presentation to the body, it means rate in minus rate out. So, yun yung formula. So, on conversion and rearrangement, K is equal to RO minus KE. Then ito. Then since X is equal to BD, so you have to replace the X to BD. So this should be the first equation for that one. And for the steady state, is the rate of change of body, is the rate of change of drug in the body is 0. So from here, this is the equation for the steady state. The steady state is equal to the rate of infusion over clearance. So this is the final formula for that one. And just take note that equation to determine drug concentration of the drug at any time, this will be the formula. And then equation to determine concentration of the drug at a steady state, this will be the formula. So ang legend nito is yung C is a concentration of the drug present in the body at time. Then CSS is concentration of the drug in the body at a steady state. Then N is the number of half-life. RO means rate of infusion. KE means elimination rate constant. And BD means volume of distribution. And CLT means total clearance. So yun lang, ma'am.
Okay. So your partner is not yet around, no?
Yes,
Dito
ma'am.
na,
Kasi
ma'am.
malakas do ang ulan.
Ay,
Ay, andito na ata.
opo.
You still have,
Ay, nandiyan ka na, Ayman. Sorry. Sige,
Yes
Ayman.
po.
you still have your part to report, no? Tama.
Yes po.
Okay,
Opo.
sige, go.
Share this. Screen. Okay, so good afternoon, classmates, and good afternoon, ma'am. Yes, so I will report about the two-compartment open model of IV infusions. Okay, so for the estimation of the drug clearance and volume of distribution from the infusion data, so the the plasma concentration of the drug during the constant infusion was described in terms of the volume of distribution and elimination constant K in the equations. So alternatively, the equation may be described in terms of the clearance by substituting for the K into the equations. So here is the equations. So where does the VD, this stands for the total of distribution, then the CN here, this is the total body clearance, and the K, which is viewed as the dependent variable that depends on the V and VD, which is here. So In this equation that is applied in the population pharmacokinetics to estimate both the CN and VD in the individual patients with one or more data points. So in this model, the time of the steady state and the resulting steady state concentration will be dependent on both clearance and volume of the distribution. So, when a constant volume of distribution is evident, the time of steady state is then inversely related to the clearance. So, thus, the drugs with the small clearance will take a long time to reach the steady state. So, fortunately, the plasma samples taken at a time equivalent to the less than one half-life after the infusion was started may not be very discriminating due to the small change in the drug concentration. So the blood samples taken at the 3 to 4 half-lives later are much more reflective of their difference in the clearance. So meaning that it is different yung sa central compartment and also sa meron siyang dalawang since it is two compartment, meron isang central compartment and peripheral compartment. So, wherein, sa central compartment, dito yung tinatawag na incoming drug in the central compartment. So, wherein, sa peripheral compartment naman, it will somehow, again, distributed into equilibrium concentration that is maintained from this two compartment. It's either na vice versa. So, in this, wherein, sa dalawang compartment na to, it has a different, um, different equations. Okay, so, next po. Next slide po. Okay, so for the intravenous infusion of the two compartment model drug, so here is the difference between the one compartment model and the two compartment model. So wherein sa X1 here, it stands the amount of the drug in the central compartment, wherein sa X2, this is the amount of the drug in the peripheral compartment. So thus the K here, stands for the K12. This is the rate constant of the drug from the central compartment to the peripheral compartment. So kapag naman K21, this is the rate constant from the peripheral compartment to the central compartment. So wherein si K dito, actually dito yung sa K12 kapag K1 1 to 2, which is the central compartment to the peripheral compartment is K1 to dito. Then, from the X2, or this is the peripheral compartment to the central compartment stands for K21. So, dito, sa K, this stands for the elimination rate constant from the central compartment to the outside of the body. While sa one compartment model is somehow parang diretso lang siya, direct. Unlike yung sa two compartment is dadaan siya from the central compartment to the peripheral compartment. Okay, so next slide po. Okay, so we have the difference between the one compartment and two compartment model. Okay, so we're in the plasma drug concentrations. So it takes na direct. Okay, so pero dito sa two compartment model, since it is before the administration, so it will somehow immediately pupunta sa central then. It will after that distribute to the peripheral compartment. Okay, so next po. Okay, so yeah. Okay. So the difference between the one compartment, two compartment model, so wherein sa diagram explained, so the drug that follows the pharmacokinetics of the two compartment model does not equilibrate rapidly throughout the body as is assumed for a one compartment model. So the central compartment represents the blood, extracellular fluid, and highly perfused tissues. So the drug distributes rapidly and uniformly in the central compartment, So the second compartment, known as the tissues or the peripheral compartment, contains tissues in which the drug equilibrates more slowly. So since natapos ko na differentiate yung central compartment and the peripheral compartment. So since the two compartment model, wherein the many drugs given in the single intravenous bolus dose, so demonstrate a plasma level time curve that does not decline as a single exponential first order process. So the plasma level time curve for the drug that follows a two-compartment model shows that the plasma drug concentration declines the bio-exponentially as the sum of the two first-order processes, that is, distribution and the elimination. So the drug in the tissues that have the highest blood perfusions equilibrates rapidly with the drug in the plasma. So these highly perfused tissues and blood make up the central compartment while this initial drug distribution is taking place. So while sa multi-compartment drugs are delivered concurrently to one or more peripheral compartments composed of the groups of tissues with lower blood perfusions and different affinity for the drug. Next slide, please. Okay, so since the drug will concentrate in the tissue in accordance with the affinity of the drug for that particular tissue, so for example, the lipid-soluble drugs tend to accumulate in the fat tissues. So the drugs that bind the plasma proteins may be more concentrated in the plasma because of the protein-bound drugs that do not diffuse easily into the tissues. So the drugs may also bind with the tissue proteins and other macromolecules such as the DNA melanin. So here is the general grouping of tissues according to the perfusion. So we have the highly perfused and slowly perfused. So the highly perfused is our heart, brain, and the hepatic portal system, kidney, and endocrine glands. Whereas slowly perfused is our bone, ligaments, tendons, cartilage, teeth, and also the hairs because it has no wala siyang circulation of the blood. Kaya that is why it is slowly perfused, unlike sa highly perfused na organs. So the model can be depicted here, shown below with the elimination from the central compartment. So there are sa two compartment models, there are several possible two compartment models. We have the model A and model B, and also the model C. So the compartment 1 is the central compartment, and the compartment 2, which is the tissue compartment. So just like what I've explained kanina. So the rate constant of the K12 and K21 represents the first order rate transfer, constant for the movement of the drug from compartment 1 to compartment 2, and from the compartment 2 to compartment 1. So which is the same first order rate transfer. Okay, so next please. Okay, so for the intravenous infusion of the two compartment model drug, so the IV infusion requires the distribution and equilibration of the drug before the stable blood level is reached. So required lang siya ng distribution and equilibration of the drug before na ma-stable yung blood level. So the distribution equilibrium, constant drug concentration in the tissue, and also no net charge in the amount in the tissue occurs during the steady state. So the time needed to reach the steady state blood levels depends entirely on the distribution of the half-life of the drug. So taken for here na the time needed to reach a steady state blood levels depends entirely on the distribution of the half-life of the drug. So equation describing the plasma drug concentration as the function of time is as follows. So here's the equations. Okay, so here is wherein the CT, this is our plasma concentration. So stands for plasma concentration. So here is wherein the volume of the distribution of the central compartment. So in other words, these are the equation describing the plasma drug concentration. So for the at the steady state, so here is the equations where A and B are the hybrid rate constant and the R is the rate of the infusion. So at the steady state, wherein the T is the equivalent to the infinity. So here is the concentration steady state equation. So for the infusion rate, by rearranging this equation, so the infusion rate for the desired steady state plasma drug concentration may also be calculated. So this. So for the loading dose of for the two compartment model drugs, so for the drug with the long half-lives are required a loading dose to more rapidly attain the steady state plasma drug levels. So for the rapid therapeutic drug levels can be achieved by using a the loading use. So the drugs equilibrate slowly into the extravascular tissues. So the drug equilibrium is not somehow immediate. So wherein the plasma drug level after the various loading dose and rates of the infusion for the drug that follows a two-compartment models. So wherein the A here, this is stands for the no loading dose. Then B here, this is stands for the loading dose, wherein over K, which is stands for the rapid infusion. So the C, this is the stands for the loading dose, wherein R is over B, which is stands for the slow infusion, while use B, which is the loading dose, R and B, which is the same with the B. So rapid infusion. So for the apparent volume of the distribution at the steady state, the two compartment model. So the volume of distribution at the steady state, wherein the VDSS is the hypothetical space in which the drug is assumed to be distributed. So the product of the plasma drug concentration with the VDSS will give the total volume of the drug in the body at that time period, such as yung CPSS times the VDSS is equals to the amount of the drug in the body at the steady state. So at the steady state condition, so the rate of the drug entry into the tissue, so the compartment from the central compartment is equal to the rate of the drug exit from the tissue compartment into the central compartment. So these rates of the drug transfer are described by the following expressions. So here is uh, the equation. Okay, so next slide, please. Okay, so because the amount of the drug in the central compartment, wherein the dP is equals to the VPCP by substitution in the equations. So for the concentration of the drug in the central compartment at the steady state, here is the equations. So for the substituting the equations, so we're in expressing the dP as the VPCP, a more useful equation for the calculation of the VDSS is somehow obtained. So here, which reduces into the VDSS is equals to VP plus K1 2 over the K21 VP. So next slide, please. So the VDSS is the function of the transfer constant K1, 2 and K21, which represents the rate constant of the drug going into and out of the tissue compartment respectively. So the magnitude of the VDSS is somehow dependent on the hemodynamic factors responsible for the drug distribution and on the physical properties of the drug properties, which in turn determine the relative amount of the intra and extravascular drug. So for the another volume term used in the two compartment modeling is the VD beta. So this VD beta is often calculated from the total body clearance that is divided by the V, unlike the steady state volume of the distribution, which is the VDSS, wherein the VD beta is influenced by the drug elimination in the beta phase. So reduce the drug clearance from the body may increase the AUC or the area under the curve such that the VD beta is either reduced or unchanged depending on the value of the B. So as shown here in the equations. So unlike the BDB, so the BDSS is not affected by the changes in the drug elimination. So wherein the BDSS um, reflects the true distributional volume occupied by the plasma in the tissue pool when the steady state is reached. Although this volume is not useful in calculating the amount of the drug in the body during the pre-steady state, so for the VDSS multiplied by the steady state plasma drug concentration, wherein the CSS yields the amount of the drug in the body. So this volume is often used to determine the loading drug dose necessary to upload the body to a desired plasma drug concentration. So as shown by the equation, so the VDSS is several times greater than the VP, which represents the volume of the plasma concentration, but differs somehow in value depending on the transfer constant. Next slide, please. So for our chapter summary, so an IV bolus injection puts the drug into the systemic circulation almost instantaneously. So for some drugs, the IV bolus injections can result in the immediate high plasma drug concentration and the drug toxicity. So an IV drug infusion slowly inputs the drug into the calculation and can provide a stable drug concentration in the plasma for the extended time periods. So for the constant IV drug infusions are considered to have zero order drug absorption because of the direct input. Once the drug is infused, so the drug is eliminated by the first order elimination. So for the steady state is somehow achieved when the rate of the drug infusion, example like rate of the drug absorption equals the rate of the drug elimination. 4 to 5 elimination half-lives are needed to achieve the 95% of the steady state. So the loading dose given as an IV bolus injection may be used at the start of an infusion to quickly achieve the desired steady state plasma drug concentration. So for the drugs that follow the two-compartment model, so the multiple small loading dose or the intermittent IV infusion may be needed to prevent the plasma drug concentration from becoming too high. So for the pharmacokinetic parameters may be calculated from the samples taken during the IV infusion and after the infusion is stopped. So regardless of whether the steady state has been achieved, so these calculated the pharmacokinetic parameters are then used to optimize the dosing for the patient when the population estimates do not provide outcomes suitable for the patient. Next. So here's our reference for our report. So thank you, ma'am. That is all my report.
Okay, thank you. Sige, you may unshare the screen. Can you give me? Ayan, sige. So let's talk about again our pharmacokinetics of intravenous infusion. But we'll not really discuss one by one the complicated na mga problem solvings, yung mga equations natin for this ha, kasi we have like limited time for the whole computation, and I believe we had this in our undergrad, no, and it will take a lot of time since most of the solutions are actually long. So let's just discuss some of the important things that we need to know about intravenous infusion and the pharmacokinetics of this one. So again, when you say IV infusion, we are administering our drug through intravenous route at a constant rate over a determined time interval. So we use this route of administration if we want to really control the plasma concentration precisely, okay? Depending on the needs of our patient. And this will be advantageous, especially in the case of drugs with narrow therapeutic index, okay? Because again, we can always control the plasma drug concentration if we are going to give the drug via intravenous infusion na route. Okay? And we can maintain an effective constant concentration, but at the same time, it will not be able to reach class the toxic concentration. So it will just be between the minimum effective concentration and the anong tawag dyan, toxic na concentration. Okay? And aside from that, electrolytes, nutrients, and other drugs can also be administered concomitantly via the infusion line of our patients, especially those that are critical and nangangailangan ng maraming drugs. Not just drugs for their condition, but like mga supplements din nila. Okay? So duration of drug therapy may be maintained or terminated as needed if we are going to use this IV infusion. Okay? So again, our aim is to maintain a plasma concentration, a flat concentration time profile. Okay? So yung mga examples of drugs that can be given via IV infusion are the following. We have the heparin, the insulin, diazepam, and our adrenergic agonists. And what are their similarity is they have short elimination half-life, and most of them are used to treat critically ill na mga patients. Okay, so this is how the concentration and time na graph looks like for our IV infusion. So definitely at time 0, there will be no drug in the body. So as you can see, 0 lahat. 0 times 0 concentration. But as we give the drug via the IV infusion, definitely there will be a rise in the drug concentration in the plasma. And that is not just it. Aside from you have the increase in the plasma concentration in the body, there will also be an increase, syempre, on the rate of the elimination. So, ano yan siya, pantayan sila mag-i-increase yung plasma concentration, mag-i-increase yung elimination rate, pero steady state concentration will be achieved at a certain time. So that's what we call plateau. Okay, so in this part here, there will be a plateau plus. That's how we maintain our steady state concentration via the IV infusion. Kasi there will be, tawag dyan, magiging proportional, so magiging equal na yung rate of infusion doon sa rate of elimination. Yun yung time na ma-achieve natin yung plateau. Okay, there is a constant drug kasi nag-i-infuse ka nga for a certain time na may time interval dyan, and then pagkatapos magiging parehas na yung rate of elimination. Okay? So again, we can maintain this one here. Ito yung talagang magiging graph ng ating concentration over time ng ating IV infusion. But if we are going to increase the infusion rate, so for example, we are not actually increasing the concentration mismo ng drug, but the rate, kung gaano natin kabilis ibibigay yung ating drug intravenously. We will also expect a new level of this one. Meaning yan, tataas yung rate, tataas yung magiging time then wherein we are going to achieve our steady state concentration. But anyway, if we are going to end or we are going to stop the infusion, definitely we are going to look at the graph. There will really be a drop since there is no source of the drug anymore, and that there will always be elimination. So that's the time wala na. Magda-drop na ito. But we will not do this kasi we need a semi-log paper for this to achieve this kind of graph. If we have class a data for the concentration, plasma concentration ng ating patient. Okay? Now, what about this? Rate of drug input represents the infusion rate and rate of drug output represents the elimination of drugs. So these two are being monitored if we are giving the patient IV infusion. Okay? So the one that will administer the drug will always see to it that the infusion rate is correct and at a normal level. And if we are going to check the output of the drug, example, the metabolite being excreted, then that will represent the elimination. But in this case, for IV infusion, this actually follows a combination of a zero-order kinetic and a first-order kinetic. If you can still remember, when you say zero-order kinetic, diba, the elimination is actually constant. So, constant sa time ha. So, if we are going to graph the zero-order kinetic, we will just get a linear na graph. Because again, there is a constant decrease. But if we're going to look at the first order kinetics, we may have a graph that looks like this. So it's not really a linear or a straight line, since for first order kinetics, the elimination of the drug is dependent on the on the concentration, okay? Concentration left in the body. This will just be a straight graph if we're going to use a semi-log paper. But then again, for IV infusion, there will be a combination of the two, the zero and the first order na kinetics. So for the zero order process, actually, this will be on the infusion rate. Kasi the drug will be administered at a constant rate. Okay, so there will be a constant amount of drug given to the patient per unit time. But the elimination of the drug in the body will follow the first order process or the first order kinetics. So that will be dependent on the amount of the drug or the concentration of the drug left inside. Okay, so initially the elimination process is actually very slow because of the low plasma concentration. Remember, at zero time, there is no drug in the body. It will just increase after the has been started. Wait. Asan na yun? Okay. No. Okay, so there again, there will be a slow elimination process. However, it will just increase as there is an increase in the infusion rate or there is an increase in the plasma concentration. Okay. Do you have questions? Or let us just continue. So we have again two characteristics of our steady state concentration for our IV infusion. This will always be equal for the rate of the infusion. So that will be the drug that enters the body, and again equal siya with the rate of the drug that goes out sa body. So there will be a constant amount of drug inside. But actually, this is actually different for different drugs. So they don't really have the same rate of output. Nakadepende pa rin sa drug natin. Okay? But we do pharmacokinetic analysis para maset natin kung paano ba natin ibibigay yung ating drug, gaano kabilis yung infusion rate natin, for us to determine also kailan natin ma-achieve yung steady state concentration, because that's very important for us to have the maximum effect of the drug for the patient. If we're going to compute the concentration, the steady state concentration, we are going to use this formula, but I will not be including this sa exam kasi this will really take a lot of time for us to finish, no? and masyadong maraming formula. So I'll just pinpoint what are the things that I'm going to include, or what are the computations that I'm going to include in the exam or the other activities. And nevertheless, we are going to use this formula, the concentration at a certain time equals infusion rate divided by the clearance of the drug, and then times 1 minus E raised to the power of, this is the I forgot the ano ibig sabihin ng, this is actually the constant, elimination constant per time, okay, of infusion. So that will be our formula. Okay, but for CSS, this is concentration sa unit time has. For example, if we're going to compute the concentration of the drug in the body after 2 hours, so we are going to use this formula. And then this is for the CSS, the steady state concentration. So if we already know the steady state concentration, we may, since ano lang siya, SIR over CL, so that's infusion rate over clearance, then pwede na natin siyang i-substitute dito. The steady state concentration, diretso na siya kapag alam na natin. Pag wala, if we only have the infusion rate and the clearance, then we'll use the formula sa taas. Okay? So, actually, we have this here. Mention ko na siya kanina, no? CSS lang nga lang yun. CSS equals SIR over CL, but we can always derive the formula depending on what we are going to compute. If we want to compute the infusion rate, so that will just be the steady state concentration of the drug if that is already known, and at the same time the clearance. And this is naman for the clearance if the clearance is being asked. So that is again infusion rate divided by the steady state concentration. So these are the parameters that we need to know for our infusion, IV infusion. Okay? Kasi again, our goal here, why do we give the drug via IV infusion, is to achieve the steady state concentration and maintain it inside the body. So we have to know how much do we give to our patient, at what rate are we going to give the drug, and we need to know syempre the steady state and yung clearance niya. Kasi again, the IR will always be equal to the drug being eliminated. Okay? So ito yung mga factors affecting our steady state concentration. So number 1, we have the clearance, which is actually inversely proportional syempre to our CSS. Okay? Pag mataas yung steady state concentration, that means there will be a lowered clearance for the drug. So the larger the value of our elimination constant, the lesser the time it takes to reach our CSS. Now half-life also, syempre, because this is almost related to clearance also, but ano siya, there is still a relationship that exists with our steady state concentration for this. So 95%, this will be true for our drugs class. The 95% of the steady state concentration of a drug will be equal to 5 times the half-life. So if we know the half-life of the drug, let's just multiply it sa 5, and then that will be the time that we are going to reach 95% of the target na steady state concentration. Okay, therefore, if the half-life of the drug changes, then there will also be a change in the time we are going to achieve the steady state concentration. And then we have the elimination rate. So kasi 'di ba, steady state concentration should be maintained so that the drug will always be in the body and it can elicit the pharmacologic action niya. So if we are going to have a large na, I mean, yung elimination rate niya mabilis, so most likely mahihirapan din tayo with our steady state concentration. Or this will be an illustration. If the dose is being doubled, this one naman is the dose of the drug, the steady state concentration will also be doubled. So this will be the illustration here in figure A. You will have the IV infusion started at 0 time, and for a smaller dose, 5 milligrams per minute, magiging dose niya ito, and then yung time or the plasma concentration, the steady state concentration will also be lowered. But if you're going to double the dose, that means madodoble din yung steady state concentration natin. Now, how about if the half-life is being doubled for our drug, that the steady state concentration is doubled also. Okay, so in this case, you have 5 milligrams of the drug, you have the same dose for the drugs. However, there is a change in the half-life. So the half-life of this one is just 2 hours, and thus the plasma concentration is just here, 8 milligrams per liter. However, if we are going to change the half-life of the drug, diba, there are like processes to do that, to increase the half-life of the drug, then our plasma concentration, steady state concentration also will be doubled. Okay? So the time required to reach our steady state concentration is independent sa drug dose and frequency of distribution, but nakadepende siya on the elimination rate for a constant volume of distribution. Okay? So, yun yung mga examples. Now, aside from that, we have here included in the factors affecting on how and when do we achieve our steady state concentration. We have here difference in the infusion rate. So, sa infusion rate is always directly proportional to our steady state concentration. That means if we are going to increase our infusion rate, our steady state concentration will also be increased. However, that is not true for our clearance, because if we are going to increase the clearance of the drug, then there will be a decrease in the steady state concentration, since we have more drugs being eliminated in the body than the amount of drug that stays inside. Okay? So we have here naman the illustration. This one is just for the input and the results na actually pinagtabi lang ito. So that's still on the IR in the infusion rate and the clearance. Now, let's talk about loading dose and IV infusion, because some doctors are doing this, especially if yung sa drug may problem tayo with, example, yung pag-achieve ng steady state concentration medyo mabagal yung sa drug natin, or mataas masyado ang clearance. So most likely they first give the patient a loading dose, which is actually an IV bolus. So when when I say IV bolus, that is a certain amount of drug being administered directly to the patient, and then as initial dose siya. Okay, just to achieve rapidly the plasma drug concentration, and then ma-achieve natin agad yung therapeutic level. But after that, the physician will direct the administration of the IV infusion, and that is to maintain the plasma concentration. So that's the goal. Pag naglo-loading dose, syempre yung ating mga physician for our patient. But that is dependent on the need of the patient. Okay? So ano yung mga examples? We have here such a dose, yung pagbibigay ng loading dose is necessary in case of the drugs merong long ang kanyang elimination half-life. So And at the same time, yung mga life-saving drugs natin, like drugs that we use for seizures, for heart attack, and diabetes, we give first loading dose, again, just to rapidly achieve the steady state concentration or the therapeutic level, and just give the IV infusion after to maintain it. Okay, so this will be the graph of the loading dose and the IV infusion. This is for the single dose. So syempre, at 0 time, since this is being injected directly and a large amount of the drug is like given to the patient. So at 0 time, you will have it here, the very large amount of drug. But syempre, the graph will be going down since the drug will always be eliminated. So kaya going down siya. However, after the single IV bolus dose, there will be the IV infusion. Okay? So just to increase the amount of the drug, and then the same time, maintain yung plasma concentration. Okay? So ano yan sila? They are given concomitantly. So plasma drug concentrations decline exponentially after loading dose. Yan yung sinasabi ko kanina na after magde-decline siya kasi may eliminate na. Pero since we have the IV infusion, mag-i-increase lang siya after. Okay? So if we're going to merge the graph of the plasma drug concentration and time for the two, this will be the graph. So we can actually achieve our steady state level immediately after giving the IV bolus, though some of them will be eliminated though, but then again, we will always be maintaining the steady state level. Okay? So this again is the example. So ito yung example, hypothetical na mga data for our infusion at the same time IV bolus. So like this one at time 0, syempre wala pa yung sa IV infusion, but meron tayong IV bolus. So we have this amount of drug. Okay? Now, since we are giving infusion, we will really see na after some time, there will be an increase of the drug in the body. And on the other side, yung IV bolus na binigay, syempre, mai-eliminate. Pero, since it's being compensated by the IV infusion, there will still be the steady state level of the drug. Okay? Pero that is for the one compartment model. So, di ba, I think na-discuss na natin yung one compartment model last time na we are going to treat the body as one, meaning if we are going to give the patient the drug, it will automatically be distributed all over. Okay, all over the body. But there are drugs that follows two compartment model. So after giving it via IV infusion, it will start with the central compartment. And in this case, since this is intravenously given, the blood is actually considered the central compartment. Now, after that, there will be the distribution of the drug to the tissues, which is considered, again, the second compartment. So examples of drugs that undergo this model or follow these models are lidocaine and theophylline. So after giving the IV infusion, it will not necessarily be distributed all over the body, but mapupunta muna sa blood tapos tissues. Okay, and then pwede siyang bumalik sa blood ulit and mai-eliminate siya when it goes back to the central compartment. Okay? So that's for the two compartment model. So if we're going to look at the graph, concentration pa rin, concentration and time of the two compartment model for the IV infusion, there will be an initial dip. And this will represent the movement of the drug from the central compartment to the second compartment. Okay? Ito yung initial need na tinatawag dyan before it gets eliminated. And then we also have the so-called multiple intermittent infusions. So ginagawa din nila ito wherein they give IV infusions for a short period of time, just like 1 to 2 hours naka-infusion yung patient, and then tapos na. And then after that, there will be the elimination period of the drug. Na nung na-eliminate na yung drug, magbibigay na naman ulit ng IV infusion. So multiple intermittent infusion yung tawag natin dyan. Okay, now why do we do this? Why do we do multiple intermittent infusions? In the case of like, we prevent the increase of drug in the body na it will achieve the toxic level. Yun yung isang reason bakit ginagawa natin. Para hindi talaga tumaas ng tumaas na kung naka-IV infusion lang siya the whole day, pwedeng tumaas ng tumaas yung concentration ng drug sa body, and then again ma-achieve yung toxic level. Pag na-achieve yun, so definitely we will expect like side effects or toxic effects. So just like our aminoglycoside antibiotics, which ginagamit natin for patients with like serious infections, yun yung intermittent natin binibigay via infusion. Okay? So, paano ba yung magiging graph nito? So, this will be the graph. So, again, there will be IV infusion first for a limited period of time. Tapos, magbibigay ng time for elimination. So, this one we have here, mono-exponential decay. Before, magbibigay ulit ng infusion na naman. So, kung nakita ninyo dito, there will be again an increase in the amount of drug in the body. So again, we do this to prevent the toxic effects of the drug if we are going to have a lot of drug in the body. So that is for IV infusion. Do you have questions or clarifications? Continue. So here, pharmacokinetics of our extravascular drug administration. And that includes, syempre extravascular, that includes the oral route, the sublingual, rectal, transdermal, inhalational, IM, and the subcutaneous. And unlike the intravenous route, what is the important thing here in terms of pharmacokinetics is yung absorption. Okay? Pinaka-importante kasi, di ba, sa IV infusion, we don't talk about absorption kasi the drug is already in the blood. So if we're going to look at the graph for our extravascular route, here on the left side, we have the single dosing. So at 0 time, there is no drug, but we will really have time for absorption. We have absorption phase first before we get to achieve the maximum concentration, maximum plasma concentration at a certain time. So we also have a max there. And then after that will be the elimination phase. Okay? The post-absorption phase na mas malaki compared to the absorption phase. So talagang bababa yung amount dyan. But most of our drugs given extravascularly are given in multiple dosing. So if we're going to look at the graph of the concentration and the time, we will have a lot of peaks in this, okay? But as you can see, there will always still be the absorption phase before we get to have the maximum plasma concentration, and then there will always be the post-absorption phase, which includes the elimination of the drug. But we will have multiple doses first before we get to achieve our maximum plasma concentration. Now, just like our intravenous infusion, this may also follow either one compartment or two compartment models. Now, for our one compartment model, we have here, ayan. So we have here, after administration, syempre the drug will be most likely on the gastrointestinal tract, and we will have time for absorption. So we have here first order absorption, the Ka, and then we only have one compartment, and that is the blood and the body tissue. So we will consider them as one. Okay, so the drug will stay there before it gets eliminated in the body. So what do we need to check here? Aside from our absorption, rate of absorption, we need to check also the bioavailability of the drug, or the amount of drug, the fraction of the drug that reaches the blood circulation, because that's very important for us to know kung talagang magkakaroon ba ng effect or hindi. Kasi syempre pag konti lang, hindi natin ma-achieve yung therapeutic level niya. Okay? So again, that is bioavailability, our FA, bioavailability factor. So, our intravenous is always considered, yung kanyang bioavailability factor, always 1 or 100% kasi diretso nga siya sa blood. But that is not true with our extravascular route. And we have a lot of factors that will determine our bioavailability, the drug itself, or the formulation of the drug, and yung route of administration niya. But again, for our intravenous, we always have 1. Okay? So we have this here, the graph of the IM and the oral. So we have the same drug here at 0 time, you have 0 concentration also. But the absorption phase of the IM is like, mas mabilis compared to our oral route, and also the bioavailability. Yung concentration, the peak will not be the same between the two. So, nakadepende din siya sa route of administration even if we have the same drug. Okay? So, how do we compute this one? Ang ating bioavailability factor is computed using the area under the curve. Okay, so that's our AUC. So like for our IV bolus, okay, the area here included in the blue line is considered the AUC, while for our extravascular route, that will be from the 0 time, from the time of absorption to the elimination. Again, that's our area under the curve. This will determine our bioavailability. Now, we have 2 types of bioavailability. The absolute one is computed using this formula, the AUC of the oral route divided by the AUC of the intravenous route times their doses. Okay? Pero baliktad ha, it will be the dose of the IV over the dose of the oral route. Okay? And then, for comparative or relative bioavailability naman, we have here the AUC of the tablet divided by the solution times the reverse of the dose. And then, itong absolute bioavailability, we are comparing it to our standard, which is our IV. Itong sa kabila kasi, sa comparative or relative, we will just going to compare one route to another. Okay? To check the relative bioavailability. Okay? So for example, here, this one is an example na problem. The following data were obtained after intramuscular and intravenous administration of antihypertensive drug. Determine the bioavailability of the drug after the IM injection. So this one again is absolute bioavailability. We have here the doses of the 2 routes. We have the clearance, the volume of distribution, and the half-life. But what we need here are just the doses and the AUC. So the area under the curve for IM is 115.5, while for the IV, that's 72.1. So again, using this formula, since we are getting the IM, so dito siya, AUC of the IM, that's 115.5 divided by AUC of the intravenous route, that's 72.1. And then yung doses nila. So dose ng ating IV is 500, dito siya sa taas. Ang dose ng ating IM is 1,000 milligrams. If we're going to do the math, we'll get 0.80. We are going to convert it sa percentage. We get 80%. So in this case, the drug given intramuscularly will just have a bioavailability of 80%. So only 80% of Mr. Drug reaches the bloodstream. Wait lang, kind of, but okay. Okay, so I may include this also sa exam natin. Anyway, this one is not really that complicated. Okay, this is just for our AUC and our bioavailability. Okay, so this is for the compartment model. So like at 0 time, you have here the absorption phase before it gets eliminated. But this one is just using a normal, itong graph na ito is just using a normal graphing paper. But if you're going to use a semi-log paper, the graph will look like this. Ayan. It's just a comparison though. Now, ito yung mangyayari again for an intravenous extravascular administration na one compartment model. So, yung gastrointestinal tract is considered outside ha. Kasi ang talagang gagawin natin na as central compartment is yung ating blood and ang ating tissues. So we really need to have the absorption first and then mapupunta siya sa central compartment and then doon na natin each check yung mga parameters. Okay? After that, the drug will be eliminated. However, this will follow first order kinetics. Most of our drugs with extravascularly given drugs follow the first order kinetics, wherein the elimination is dependent on the amount or the concentration of the drug left inside the body. Now, yung absorption, ito yung mga mga informations lang that we need to know sa absorption of the drug na nag-undergo ng one compartment or nagfa-follow ng one compartment model. So equation for determining the plasma concentration at any time, ayan, chine-check natin yan. Dinedetermine din natin yung half-life and yung rate constant or elimination rate constant of the drug. And then at the same time, kasi itong dalawa nasa intravenous din. Now, aside from that, and the T1 half, kailangan din natin yung absorption rate constant. Malaman dito. Okay, just to have a whole picture of the pharmacokinetic of the drug being administered extravascularly. And at the same time, si volume of distribution hindi mawawala. But anyway, si volume of distribution is just like a model also, an approximation for us to see kung nasan na yung drug sa body natin. And then the Tmax and the Cmax are still included in the parameters that we need to consider for the extravascular route. Okay? But I think I will not be having this formula, and the computation. Let me check. So this one is also complicated. This is actually used to compute for the concentration in the plasma for our extravascular route. Let me check first. This is our formula. Concentration at a certain time equals F. Huwag na natin ito tingnan para dili pakulbaan. We have F, which is our bioavailability. So we need our bioavailability here. And then the S here is the salt correction. The D is the dose. Ka is our absorption rate constant. And then, syempre, V is the volume of distribution. And then the K only is the elimination rate constant. So, naulit lang naman yan. This will be exponent. So, multiplied with this one. negative KT, and then sa kabila, negative KAT. Okay, that's two different things. The other one is absorption rate. The other one is elimination rate. So if we are going to compute this one, let's just have one example. A 70-kilogram male patient has been administered a single oral dose of 100 milligrams of an anti-malarial drug as a prophylactic treatment. So the drug has the following pharmacokinetic parameters. The T1 half is 8 hours. The absorption rate constant is 1.5 per hour. And then the volume of distribution is 10 liters. And then itong F is the bioavailability. So assuming that this drug follows a one-compartment kinetic model, what will be the concentration at 12 hours after the dose? So please take note of this, formula. Again, we have this formula. We are going to use this if we need to compute for like the concentration of the drug inside the body at a given time. So this time, it will be 12 hours. After 12 hours, ilan na lang yung nasa body na concentration. So, isubstitute natin yung mga given. We have here, what is this? SF dKA over VD times KA. This is a different thing, right? Wait lang, let me check. Parehas lang pala. Okay. And then, what is this? We have 1.5. Wait lang ha, wala akong. Nagkabaliktad lang ito. Ay, ba't ayaw? Wait lang, mag-draw lang ako. Ayan. Sige. So this 1.5 here is, what is this? You have the KA. Yeah, this one is the KA. Nagkabaliktad lang, hindi lang siya nakapasunod sa SFDKA. And then 0.65 is our F here. And where do we get our 100? Wait lang, let me check. This one is the dose. So there is no self-correction here. If there is no given, then that is automatically 1. And then the volume of distribution, this is the VB here. This 1.5 again is our KA, so that's checked. And then take note that there is no elimination rate constant given in the problem, but there is T1 half. Now, I don't know if we can still remember that T1 half is computed using this formula. Ay, wait, i-type ko na nga. T1 half is computed using this formula, 0.693 over K. So if we're going to derive our formula, this will just become K is equal to 0.693 divided by T1 half. So if we are going to divide 0.693 divided by these 8 hours, okay, this is the T1 half, we get the 0.087. Just in case magtaka kayo saan galing yung 0.087, hindi naman siya kasali sa given. Okay? So again, walang S ha kasi this is for the salt correction only. Then it's not needed here in the problem. So everything is being substituted. We have exponent negative 0.087. Again, that's the K. And then the T here is the time. So what we are computing here is the concentration of the drug left in the body after 12 hours, after giving the drug extravascularly. Okay, the single oral dose. So in this case, from the single dose administered na 100 milligrams, we are going to do the math after 12 hours, 2.4 milligrams per liters na lang yung concentration na maiiwan. Okay? Do you have questions? I will not include this anymore. This is just for the Tmax. Let me check. Wala na ito. Okay. So let me just end here sa problem. Okay, again, this is our formula we follow for the extravascular route to compute for the concentration of the drug per given time. Okay, so I guess that's it.
Hello, good evening. Good afternoon. Good afternoon, Ma'am Risa and classmates. Our report together with Mr. Adrian. Marinig po ako.
Yes.
Okay. Um, our report together with Mr. Adrian Gales is about pharmacokinetics of IV bolus injection. I will be reporting our joint report because Mr. Gales has a parang low internet. Okay. To start, pharmacokinetics of IV bolus injection. What is an IV bolus injection? A drug is administered as an injection of a sterile solution formulation which is injected all at once. It ensures that the entire administered dose reaches the general circulation. The drug distributes instantaneously and homogeneously throughout the compartment. Drug elimination also occurs from the compartment in first order fashion. Unlike a standard drip IV, where the fluid line is closed, an IV bolus has an open line. Excuse. Consequently, the fluids enter the body at a much faster rate. IV bolus dosing. Starting an infusion at the rate required to maintain steady state is inefficient. For any desired plasma concentration, it will take 3 time constants for a continuous infusion to reach this concentration. If the half-life is long, then achieving a therapeutic level will take some time. A bolus dose aimed to fill the volume of distribution will allow steady state to be reached immediately. So the, the formula is loading dose equals volume of distribution times the concentration target. So pharmacokinetic factors affecting rate of onset. So distribution. High volume of distribution will decrease clearance from central compartment. Factors affecting volume of distributions include ionization. Ion trapping can cause drug to be sequestered. Protein binding, lipid solubility, speed of distribution, organ blood flow, metabolism, route of clearance, organ dependent, organ failures, extraction ratio, organ blood flow, saturatable kinetics, zero order kinetics, presence of active metabolites. And then in the elimination, route of excretion of active drug or active metabolites, and organ failures. So what is a compartment? A compartment is in pharmacokinetics is an entity that can be described by a definite volume and a concentration of, of a drug contained in that volume, which may be first, central compartment. The central compartment includes blood and the highly perfused organs and tissues such as heart, brain, lungs, liver, and kidney. In these organs, this administered drug usually equilibrates rapidly. Second, peripheral compartment. This compartment includes those organs that are less well perfused, such as adipose and skeletal muscle, and therefore the administered drug will equilibrate more slowly in these organs. And third, special compartment. Drug access to some body parts such as the cerebrospinal fluid and central nervous system in controlled by the structure of the CNS blood capillaries and the outermost layer of the neural tissue. So one compartment open model, intravenous bolus administration. It is the simplest way to describe the process of drug distribution as well as elimination in the body. The one compartment open model with IV bolus administration is the simplest pharmacokinetic model. So the IV dose is equals to volume of distribution, then elimination. Consider a single IV bolus injection of drug X. As time proceeds, the amount of drug in the body is DC over DT is equals rate in availability minus rate out elimination. So since rate in or absorption is absent, the equation becomes DC over DT is equals to negative rate out. If rate out or elimination time derivative follows first order kinetic, an order of chemical reaction in which the rate of the reaction depends on the concentration of only one reactant and is proportional to the amount of the reactant. So this is a formula, rate of change of CP versus time. So dCP over dt equals negative KEL times CP. So integrating this formula gives this one where CPT is the concentration at any time and the CPO is the concentration at time 0. Then times E raised to the power of negative ELT. Sorry. K is the elimination rate constant. So multi-compartment models, intravenous bolus administration, two-compartment open model, the plasma level time curve of a drug that follows a two-compartment model shows that the plasma drug concentration declines by exponentially as the sum of two first-order processes, distribution and elimination. This is attributed to distribution of the administered drug between the central compartment and tissues, which is the peripheral compartment. So in this, ang two compartment ang central and ang tissue compartment ang then the construction of the plasma level time curve for a drug that follows a two-compartment model indicates that the curve may be divided into two phases, a distribution phase and an elimination phase. For most two-compartment models, the elimination occurs from the central compartment model. So two-compartment open model, the mathematical expression that best describes the two-compartment IV bolus is CP equals A that E raised to the power of negative 80 plus B that E raised to the negative of power of BT. So, yun yung diagram. Yun lang, reference basic pharmacokinetics concept and some clinical applications. Thank you.
Okay, thank you. Wala partner mo, no?
Nandyan po siya pero mahina po ang signal niya. So
Okay,
binasa ko na lang din.
sa kanya.
Apo. Yes po. Thank you.
So let us finish this. This will just be very quick. So let's have the intravenous bolus injection. This one is, na-mention ko na siya kanina. Kasi kanina IV infusion, we are giving the drug at a constant rate, no? Given the given amount. Okay, so sa bolus naman, we are really giving the entire dose at the same time for our patient. So the concentration, of course, the maximum concentration, of course, at 0 time talaga. Kasi buong drug yon binigay na natin sa patient natin. So automatically ma-achieve na natin yung Cmax at 0 time pa lang. However, syempre the drug gets eliminated in the body, so there will be a decline in the curve if we're going to graph concentration versus time. And most of these drugs follow first order process or first order kinetics in terms of the elimination. So ulitin ko again, pag first order kinetics, the elimination is dependent on the concentration or amount of drug left in the body. Okay, so actually this is the simplest of all the routes of administrations that we have in terms of pharmacokinetics, since the drug is directly given in the bloodstream or administered in the bloodstream. So therefore, we don't need to consider absorption rate and all the things about absorption. So automatic kasi diretso na yung drug in the blood. So if we are going to look at all the formula that we have in the computation, ito yung mga formula that we encountered during our BS Pharma or undergraduate years. Kasi nga, ito yung pinaka-simple sa kanilang lahat. So yung maaalala natin na formula dati, ito na yon. So like if you're going to compute for the concentration of the drug in the plasma, we will just need the dose and at the same time, the volume of distribution. Okay, so that will just be dose over V. This one is just comparison between a graph for a single bolus injection and this one naman is for the multiple dosing. So definitely, like at 0 time, you have the maximum amount of drug, but it will decrease after some time because of elimination. But then again, if you administer another dose, then there will be an increase in the plasma concentration. Again, this will just be a comparison of the two. Now, for the one compartment model, if we are going to inject the drug, the entire dose of the drug at the same time, and if it's one compartment model, then the drug will just be distributed all over the body. We will just treat the body as one. Okay, so walang mga ibang compartments. So again, the drug gets administered and it will go to this compartment, one compartment only, the body will be distributed and then after that, eliminated. Okay, so again, most of the drugs follow first elimination rate kinetics here. So ito yung talagang first na formula na tinuturo sa atin. This one, the AP, this is the amount of drug at a given time equals the concentration or the amount of drug at 0 time, exponent, that's E, raised to the power of negative K. K is our elimination rate constant, and T is the time, the given time, kung ano ba yung hinahanap natin na time. Okay, so again, that's A. A is the amount of drug. If we are going to use the C, that means the concentration. So you may use this one also if it's the concentration that we are looking into. Okay, so this one is the representation again of the plasma drug concentration versus time after a single IV bolus. So since this follows first order kinetics, we will not have a straight line or a linear graph here because of the decline due to the elimination of the drug. However, if we can still remember our college days wherein we are asked to graph this one in a semi-log paper, then that's the time we get this one, the linear na graph. Okay, so the slope will be the elimination rate constant, which is computed using this formula. Okay, KE is equal to 0.693 over the half-life. Or pwede ding i-derive, half-life can be computed using the formula. Half-life is equal to 0.693 over the elimination rate constant. So let's have an example sa pharmacokinetic parameters for our single IV bolus dose. This one is for the gentamicin. The dose given is 200 milligrams and the volume of distribution for our gentamicin is 20 liters. Now we are going to compute the concentration at 0 time. So again, we have a not really complicated process here since we only need this formula. Concentration again at 0 time is equal to dose over the volume of distribution. So that is just 200 milligrams divided by, this is our dose here, divided by 20 liters, which is our volume of distribution. So our concentration at 0 time, the drug given sa patient natin via IV bolus injection is 10 milligrams per liter. That's the concentration in the plasma at the beginning. Now, ito naman kung i-compute yung elimination rate constant. But if you can still remember, we need like data here na marami for the concentration and at the same time the corresponding time for us to compute the KE. Okay? So like, diba, we have the negative KE is equal to, I forgot what's the meaning of LN sa calculator. And this is concentration, the concentration 2 minus concentration 1. So we need to pick here concentrations and then their corresponding time. So sa baba, that's T2, that's time T2 minus T1. But I don't know if this is the same formula that you used during college days, but we can use this formula kasi if I can remember it correctly, we use this formula during college. This is the log of the concentration minus the log of C1 over like P2 minus P1. Okay? So, yan yung maalala ko na ginagamit dati, but that's the same formula. Okay. So, what about this? This is another example. Dose is 200 milligrams. The volume of distribution is 20 liters. And ang KE, this is the same. Ito yung computed KE kanina. Given this, ito yung given in the problem na ito yung mga concentration at a given time. So yung computed na elimination rate constant is 0.25 per hour. So if we are going to compute the concentration left in the body after 2 hours, we can use this formula. D over V times exponent raised to the power of negative KE, that's the elimination rate constant, and the time. So 200 milligrams, that's just substitute divided by 20 liters. And then we have E raised to the power of 0.25, again, is the computed elimination rate constant. And then this 2 is the time. That's what we are looking for, the concentration of the drug of the gentamicin after 2 hours. So doing the math, 200 divided by 20 is 10 times this one is 0.67 here, the red one. Then multiplying the 2, we get 6.07 milligrams per liter. So diba at 0 time, the concentration is 10 milligrams per liter, but after 2 hours, ito na lang ang naiwan. That is for gentamicin. Okay, this follows again first order kinetics in the elimination, and then the drug is given via IV bolus. Okay, and for the VD, we may actually use the same formula depending on the given. So we have here, if we know the dose, the elimination rate constant, and the concentration at any time point, then aside from the volume of distribution, we can also compute for the clearance. Ito sa volume of distribution ito. So CT is concentration at any time. In this case, we have known from the previous computation that after 2 hours, only 6.07 milligrams per liter of the drug will be left. And then we know the concentration at 0 time, right? We have 10. And then ito yung magiging formula, E raised to the power of KT. Okay? But in this case, yung pabaliktad kasi ito. So kunwari, hindi natin alam yung volume of distribution. So itong concentration at zero time, di ba, we may compute that one using this formula here, D over B. Kaya sinubstitute na lang siya. This is D actually over B. So D is the dose, that's 200 milligrams. And the rest are given. K is 0.25. So this one will just be like a form of checking that everything is actually correct since we get the same volume of distribution from the start, and that is 20 liters. Okay, and then for the clearance, we may use this formula. If you know the volume of distribution already, this is the formula to get the clearance. So clearance is equal to the volume of distribution times the elimination rate constant. So that is just 20 liters times the elimination rate constant is 0.25 per hour. Okay, so the clearance here is 5 liters will be cleared or eliminated in the body per hour. Okay, so again, please take note of the different formula that we have. And then for our T1 half or our half-life, we will just use this formula. Half-life is equal to 0.693 over the elimination rate constant. So that's 0.693 over the given. This is already given in the problem, 0.25 per hour. So this will be the half-life. So again, in the case of IV bolus dose, especially for single compartment, we will just go back to the basic computations that we have in our bachelor's degree. Itong formula na ito will be used. Again, concentration at the given time equals concentration at zero time times e raised to the power of kb. So always remember this concentration at zero time can be computed using this formula, dose over the volume, just in case hindi siya given automatically in the problem. Okay. Pero like sa exam, syempre hindi ko na kayo ipapaplat like sa mga graphing paper and sa my lab. Yung mga ano lang, basic na computations na tayo with this. Like computation of the concentration at zero time, the volume of distribution, the KE, and the T1 half, and the clearance also. Okay. So I think that's the end of our discussion. Do you have questions before tamani hapon? Before tamani hapon na gabi na. Wala.